the different mathematical models involved in the theory of computation. And we started about the first mathematical model, which is nothing but a finite automata. And the basic concepts behind the theory of computations. Okay, that is automata theory. So now we have to get into more into the finite automata and regular languages, and we shall touch about the context-free grammar, that is the next enhancement of the regular expressions, and the equivalent mathematical model, the pushdown automata, that is the advanced version of the finite automata, the next incremental model of the finite automata, which is called as the pushdown automata. All these things we will be discussing, and I have collected some gate question regarding this finite automata, regular languages, and context-free grammar, and we will be discussing how the solutions will be for the questions. Okay, so let us start my presentation. Is the screen is visible?
Yes, ma'am. Yes, ma'am.
Yes, thank you. Anybody can tell at what point we stopped in the last week? Anyone? Okay, I will say. So last class we stopped with the different types of finite automata is there. One is called as the deterministic finite automata. Another one is the non-deterministic finite automata. And there is the difference between deterministic finite automata and the non-deterministic finite automata. Okay. The deterministic finite automata, as its name says, every transition is deterministic in the sense from a state on an input symbol, we can go to only one state. So the output is very deterministic. Okay. So if the DFA is practically implemented, then the machine won't get any confused about the input. Okay. With respect to every symbol, it will give the proper output. But in case of the NFA, there may be the chance of the empty transition, in the sense that may transition on the input symbol from any state. Similarly, from a state on a single symbol, there may be more than one output transition is there. More than one output in the sense that by reading a single input symbol, if there are more number of paths, then automatically the machine will get confused. As a design purpose, the NFA is very simple, but the practical purpose, the DFA is only implemented. That is the difference between the NFA and DFA. And we have seen how the DFA model and NFA model will look like, okay, and how we can represent. There are two forms of representation of DFA and NFA. One is the diagrammatic representation, and other is the table representation. I think in last class I have shown how the diagram and table will be look like. For example, this is the diagrammatic representation of a NFA. The equivalent table representation is given below. There are two states. You assume that the states are the circle or called as the states. Okay, there are two states, Q0 and Q1. Normally the states are named Q0, Q1, Q2, and like that. The initial state is named as Q0. Okay, so this is the normal convention. So initial state is indicated by the arrow. Normally the double states, the final states are double circled. Okay, and here with the labeled transition, okay, you see some labeled transition. The label over the directed edge is called as the input symbol, and there are two input symbols here. One is 0, another one is 1. Okay, so based on this diagrammatic representation, here we can write a table representation also. In table, there is a row and column. In every row, we have the states, and in every column, we have the input symbol. Okay, so there are two rows because there are two states there, Q0 and Q1. And in each cell, okay, which is I'm highlighting by yellow color, in each cell, you have to write the output with respect to the state which is in the row and the input is in the column. Okay, for example, the first cell, which is I'm highlighting by means of, you understand, this is again blue. Okay, so this is the cell. Now I'm concentrating. So this cell tells what is the output transition from Q0 over 0. So Q0 over 0, there is two output is there. From Q0, the 0 symbol goes to Q0 as well as Q1. So there is a 2 output. Then from Q0, the 1 output is going to Q0 only. From Q1, there is no outgoing transition is there. So we are simply highlighting that, indicating that by dash. Okay, this is the null transition. Okay, so this is the table representation. Okay, So the next important function is the extending transition function. So why we have to extend the transition function mean normally the transition function tells how the finite automata will behave over a input symbol. But the purpose of designing the machine is to validate the language. Okay, in last class we discussed what is language. The language is nothing but a set of strings. And string is also we discussed the string is nothing but the collection of input symbol, a sequence of input symbol of any length. It may be a length 0, which is nothing but a epsilon. It is an empty string. Length 1, length 2, likewise, you can have the string of any length. The collection of strings of the same alphabet is called as the language. Did you understand? Okay. So the purpose of designing the DFA is to validating the language. That is the main purpose. Okay. So in order to validate the language, what we have to do? We have to validate all the strings of such language. So we have to extend the power of DFA, how it can validate the string. Because normally we design the DFA or NFA in order to having the transition over the single symbol. So like here we have the diagram. So in every transition, we have the transition over a symbol only. Did you understand? But now we have to extend the power of the finite automata. That is called as the extended transition function. Normal transition is defined by, that is indicated by the letter del, and the extended transition function is indicated by the letter with the convention del star or del cap. Anyone you can use del cap or del star. Okay, and this is the general form of the del star, and del star is equal to q cross sigma closure tends to q for DFA. Okay, so because the transition function takes two arguments, you know, the first argument is always the state. Okay, the second argument in normal del is the sigma alone because it takes only the input symbol. But here, the in extended transition function, the second argument is the string. The string is nothing but sigma closure. Why closure? Closure is nothing but 0 or more occurrences of any. Okay, because we already discussed the string may have any length. So it is sigma star. Okay, sigma star is nothing but sigma closure. It is nothing but the any length of the symbols in sigma, which leads to again Q, because here it is a deterministic output. Always we end up with the single state. Okay, and this is a formula how we are making the del cap transition. Okay, so we define the formula in two. One is for epsilon. Epsilon is nothing but how the DFA behaves over a 0 length string and how the DFAs behave over the n length string. So in for n length string, you have to divide the n length string into n minus 1 length and 1 symbol. Why means because in the diagram we have the provision to making the transition over a single symbol. But by doing these transition continuously, definitely we can process the string. That is the ultimate purpose. And we shall have the example for that. You see, so this is your DFA, for example. And this DFA has 4 states, and this DFA is defined over the input symbol 0 and 1. But now my task is I want to check the string 0, 1, 0 is accepted by this DFA or not. Okay. How can I do this job? Okay, in order to check the validity of the string, how can I do it? I have to start my process from the input state, which is nothing but Q naught. From Q naught, I have to read a first input symbol. What is that? The first input symbol is 0. So from Q naught, where the 0 is going, it goes to Q1. Then from Q1, I have to read the next input symbol, which is nothing but a second input symbol. The second input symbol here is 1. Okay. The second input symbol here is 1. You see? So from Q1, I have to read 1. From Q1, the 1 goes to where? It goes to Q2. Okay. So in that state, I have to read a third input symbol. What is my third input symbol? That is also 1. So from Q2, the 1 goes to Q1. Then from Q1, I have to read a fourth input symbol. What is that? It is 0. From Q1, the 0 goes to Q0. Okay. So finally, I end up with the Q0. Okay. So once I reach the last stage, I have to check the status of the state, whether that state is a final state or non-final state. Okay. So I already said the final states are double circled in the diagram. Okay. If you are representing the DFA or NFA in table, the state is preceded by some star symbol indicating such states are final state. But here it is a diagrammatic representation. So the states are double circled. So here only Q0 is double circled. So according to the convention, the Q0 is the initial as well as the final state. Okay. And after processing 0, 1, 1, 0, we end up with Q0. It says the given string is valid. Once we end up with the final state of any final state, okay? Because the DFA may have any number of final state with respect to the definition, we may end up with any one final state, okay? So whatever final state we end up with, we immediately conclude that the given string is a valid one. So for the answer for the question is, yes, the string is accepted by the DFA. This is the answer for the question. So by shortly, I tell how we are making the processing, but this is the overall process you have to do with the help of the notation, okay? Actually, del star you have to do. Del star is nothing but a string processing. From where you start your string processing? From Q0, okay? From Q0, you have to start your string processing. What is the string you have to process? 0110, okay? That is you have to process. Did you understand that? Okay. 0110 you have to process. By processing that, you end up with Q0. And since Q dot is accepting, we say that it is valid. Did you understand? So now we have to look into the designing of DFA. So why I am interested, this means because in most of the questions in GATE, they are given the language, then they asked that what is the minimal number of states required in order to validate such language. So for that, what we have to do is we have to design the DFA for the given language, and then we answer this is the number of states required in order to validate the language. That will be the answer for the question, okay? So for example, I'm taking very simple example first. Design a DFA which accepts the string, okay, only one string, 00, over the input sigma equal to 0, 1. Okay, what are the steps we have to follow? Means actually for the designing of DFA from the language, there is no prescribed procedure is there. We have to apply our own logic, okay, in order to validate all the strings of the language, okay, to design the DFA. But some simple step, okay, these are called as hidden steps we can follow. What does that means? For any language given, we have to write the strings of all the language, okay, because you are provided with only the language, okay. What is language actually? Language is a set of string. Write some strings starting from the basic string. Basic string is called as the minimum length string, which is called as a basic string of the language. You start writing the strings of the language from the basic string up to some length. That is up to you. You can write some strings and identify minimum number of states needed to recognize the basic string, okay, because among the number of string, only one string is the basic. Basic string is nothing but a very first string in the language of the DFA. Then we have to start the design of DFA with the minimum state, okay. So add the transition to each state on every input symbol to accept other strings of the language. If some valid strings are not accepted by the minimum states, then we have to add more number of states and transition in order to accept all the strings. We should not leave any one string, okay. For that, we have to add a state and transition, and after then we have to decide about the final states of DFA. So here the question is, you have to design the DFA for accepting 00. So in order to design the DFA to accept the string, what you have to do is you have to facilitate the path from initial state to final state over such strings of the language, okay. We are saying some strings are valid for the DFA. How we are saying that for the string, there is the path from initial state to final state. If you are facilitating such a way, then we can say the string is a valid one, okay. So this is actually the DFA required in order to validate the language L, which consists of only one string 00. This is for a simple purpose I'm taking. So the language only consists of one string, because we say the language is a set of string. Okay, the set may consist of a single member. Okay, that is no restriction at all. Okay, here the string consists of language consists of only one string, which is 00. So in order to recognize this 00, you have to make a path from initial state to final state over the 0 and 0. Okay, so I'm saying this Q0 is the initial state. From Q0, I add a transition over 0 to one more state, which is called as Q1. Okay, so on reaching Q1, I read only one symbol 0, but I have to read one more symbol 0 in order to reach the final state. So what I have to do is I have to read a next input symbol 0 from the state Q0, Q1 to Q2. Okay, and I make this Q2 is the final state because on reaching this state, I already read two zeros. 2 zeros is a valid for my language. So it is enough. Okay, so here the basic string is called as the first string of the language. Only one string is here, that itself the first string. So what is the length of the basic string here? What is the length of the basic string? Anyone? Only one string is here, that itself the basic string. What is the length of this string? What is the length of this string? How many symbols in it? The length is called as how many number of symbols in the string. According to that, what is this? Anyone? That is 2. Okay, there are 202. That is the length of the string is 2. So in order to validate the string of length 2, at least 3 state is required. Okay, if the string length is n, there should be n plus 1 state is required in order to validate. Okay, so this you have to keep in mind, because with respect to this relation, there are several questions asked in the gate. Okay, so you have to keep it in remember. Okay, so these are some of the example I have taken. So design the DFA which accepts 0 or more occurrences of A. What do you mean by 0 or more occurrences of A? Anyone? Zero or more occurrences of A. What do you mean by 0 or more occurrences of A? What is the language? 0 or more occurrences of A means, what is the 0 occurrence of A? 0 occurrence of A means it is epsilon. 0 occurrences of A means that is epsilon. Okay, 1 occurrences of A means A. 2 occurrences of A means AA. 3 occurrences of A means 3A. Likewise, it goes because it is a 0 or more occurrences. This is the infinite language. In the previous example, we have seen the finite automata that accepts only one string. Now the case is different. You have to design the single machine that should accept all the strings of this language. This is the infinite. Did you understand? But you are going to design a single machine. Okay. So how many state is required? Anyone? Do you have any guess? Should be interactive at least. Then only it will be helpful for me whether you will be understanding or not. So this is actually the language. Okay, epsilon A, and 3A likewise it goes. Okay, so what is the minimum number of state is required is only one state. Why means epsilon is there. There is a basic string. In order to accept the epsilon, definitely the input state itself a final. Do you understand? Okay, so in order to accept the epsilon, definitely the input state should be a final. Then only we can accept epsilon, because epsilon means without reading any input, you have to go to the final state. How it should be possible in a DFA? By making the initial state itself a final, then only it is possible. And on the initial state, you can make a self loop over A. Okay, so this self loop facilitate any number of A you can read according to your string. If I have a string of 2A, I have to read 2 times A on the from the state Q0. So I can read and validate AA. Similarly, whatever number of A's, that amount of times you have to self-iterated. Did you understand? This is the DFA. Okay, so take a next question of design the DFA which accepts one and more occurrences of B. One and more occurrences means that at least one B is there. Then afterwards, you can have any number of B. So 1B is a minimum length string, 2B, 3B, likewise you can. Okay. So what is the DFA required is at least 1B you have to read. Do you understand? That is at least 1B you have to read. So you have to make a 2 state. Why 2 state means that here the basic string. What is basic string? That is the minimum length string in the language. Which is the minimum length string? B. B is itself a minimum length string because it has the length 1. Okay. So if the basic string has length n, you require n plus 1 state at least. I'm not saying exactly n plus 1. At least n plus 1 state you require. So you can apply this formula in the previous also. Here, what is the minimum length string? It is epsilon. Okay, what is the length of this epsilon? 0. Okay, so at least how many state you require? 0 plus 1, n plus 1 I'm saying as a relation. So 0 plus 1, 1 status you require. This is for at least, not exactly. So kindly keep it in mind, because they are playing with the word. When there is a question in the gate, they are playing with the word. Okay, whether n plus 1 exact state or n plus at least n plus 1 is required. Okay, such kind of question may be asked. So you have to keep in mind that this is at least n plus 1. So here the basic string is B, that is a single length string. So at least two states we require. I'm calling those two states are Q0 and Q1. I make an explicit transition from Q0 to Q1 over B. Then on Q1, I can make a self loop. Why I am making self loop? Because it is any occurrences of B. Did you understand? Okay. So whatever string you will be provided, based on that you can read any number of B, and you have to make this Q1 as a final state. Okay, so the next case. Okay, so we have to make a complexity in an incremental way. The next is example is we have to design the DFA which accepts those strings which are started by 1 over sigma equal to 0 comma 1. So first you have to identify what are the strings of the language. If you fail to identify the strings of the language, definitely the DFA design will be the question mark. Okay, so this is the first step where definitely you have to write a language in a correct way. Language is nothing but a set of strings. How you are framing the string according to the constraint given in the question. So here what constraint you are provided with? Here the alphabet is 0 and 1, and the string is a combination of 0 and 1. Okay, but the condition is all the strings should be started with 1. All the strings should be started with 1, and there is no condition on the length of the string. Okay, kindly understand, there is no condition on length of the string. So the minimum length string is 1, and in length 2 you can make a string, in length 3 you can make a string, in length 4 you can make a string, likewise it goes. So this is also the infinite language. In length 1, what is the string? 1. Okay, the symbol is 1 because the constraint is the string should be started with 1. In length 2, we can make two strings. They are 1 0 and 1 1. Okay, because you know in zeros and 1 combination you can make how many strings in length 2? 0 0, 0 1, 1 0. Okay, 1 0 and 1 1. These are the combination you can make, but all the 4 cannot be included here because the constraint is the string should be started with 1. So we are eliminating this 0 0 and 0 1. We are eliminating only these two strings in length 2 can be included. Okay, did you understand? And similarly in length 3. Okay, so in length 3, you know how many combinations are there? There are 8 combinations. Among the 8 combination, we are removing the strings which are started with 0. Only the string which is started with 1 can be included. Okay, this can be actually included. Okay. Okay, the 4 strings can be included. Is it okay? So according to that, now we have to design the mission. Okay, so here the basic string is actually 1. If basic string is 1, the length of the string is also 1 because there is only one symbol is there. So the minimum number of states required is 2. Okay, they are Q0 and Q1. From Q0 to Q1, there is the one transition. From Q1 to Q1, here please see that the transition over 0 and 1. Y means only the first symbol is 1. Okay, but second, third, fourth, fifth, and likewise, whatever number, it may be 0 or 1. Whenever the word or is come, okay, maybe 0 or 1 or. Whenever the word or is come, you have to write the two inputs, 0, comma 1. Comma here means or. Comma means here or. Sometimes comma may be represented by plus also. Okay, addition operator plus. Okay, that is also the interpreted as or. Okay, so this is the design of the DFA which accepts the string. They are started with 1 and followed by any number of zeros and ones. Okay, so here see the next mission. Design the DFA which accepts those strings which are started by 1 and ended by 0. Okay, one more condition, started by 1 and ended by 0. So at least in length 2 you can make a first string. In length 0 we cannot make, length 1 we cannot make. At least in length 2 we start the string. Okay, So here the basic string is called as the first string of the language. Okay, 10 is the first string of the language. Okay, only one string you can frame in length 2. Why? Because length 2 we can have 4 strings: 0 0, 0 1, 1 0, and 1 1. 0 0 we cannot include because it violating the condition. Why means the string should be started with 1. That is the condition given. So if you are included 0 0, it is violating. So we are excluding it. Next is 0 1. 0 1 is also violating because the string should be started with 0. Okay. And 1 0 we can include because the string is started with 1 and ended with 0. And 1 1 we cannot include because this condition given is the string should be ended with 0. But in 1 1 the string is ended with 0 1. So we cannot include. Okay. So with respect to the condition, we can include the strings in length 2, length 3, length 4. This is also the infinite language. Okay. So tell me, what is the minimum number of states required in order to validate this language? Anyone? Kindly reply me. Then only I can understand. Anyone? What is the minimum number of states required in order to validate this? I will show the question, then you can understand. Okay, why we are seeing this number of examples, because based on that there are several questions. Anyone? What is the minimum number of states required in order to validate this entire language? The minimum number of states, at least minimum number of states, that is determined with the help of the length of the basic string. Okay, I already say if the length of the basic string is n, at least you require n plus 1 states. Okay, here what is the basic string? Basic string is nothing but the first string of the language. What is the basic string here? Anyone? What is the basic string here? I said it is the first string of the language. Am I audible first? Am I audible?
Yes, ma'am, I'm audible. Audible, ma'am.
So only ma'am is answering. What about the students? Anyone? What is the
Audible,
basic?
ma'am.
Yes, what is the basic string of this language? Tell me, what is the basic string? What is the basic string? Yes, the basic string is the first string of the language. Here, what is the first string? I'm writing so many strings for this language L. What is the first string here? What is the first string? Anyone? I'm not asking you a complex question. I am writing the entire language. I'm just asking what is the first string of this language. That's all. What is the first string of this language? Is the things is clear to you? Or the things are clear?
Students, please be interactive. Please, if you have any doubts, please ask. Do you want to explain it again? Is the concept is clear? Please be interactive in at least in chat box. Please be interactive. It's like one-way communication. Agnes, Akhila, Anita, Anushya, are you all here?
Arul Karthik, what is the first string of this language?
Length string, ma'am.
First string. I'm asking you the first string of this language. I have written this language. I have prepared all the questions for it. This is the language. Language is a set. What is the first string? I'm asking just what is the first string. You see and tell. What is the first member? What is the first member of this set? Arul Karthik, are you in the line?
Yes, ma'am.
What is the fastest member of this set? I'm highlighting one set. Is a
1
three
0,
digit
ma'am.
1 0. 1 0 is the first member. That is the basic string or the first string of this language. Okay. So if this is the first string, okay, what is the length of this string? Tell. What is the length of the string?
8, ma'am.
Your string is 1 0. What is the length? Your string is 1 0. What is the length of 1 0? What do you mean by length of the string? What do you mean by length of the string? If the name of the student is Ram, okay, what is the length of the name Ram? Arul Karthik?
2, ma'am. 2.
Ram, R-A-M. What is the length of the name Ram? What do you mean by length? How many number of letters in the name?
Characters.
Yes.
Yes,
what
ma'am.
is the number of characters in
Ram
Ram?
ma'am.
Yes, in Ram.
5, ma'am.
Ram, R-A-M. Only 3 letters. So the length is 3.
WRONG, ma'am.
What is that?
WRONG தான கேக்குறீங்க?
Ram, R-A-M. R-A-M,
3,
Ram.
3, ma'am. 3.
3. So similarly, here I'm asking what is the length of the string 1 0?
2, ma'am.
2. So what is the minimum number of status required to design DFA? You tell me the relation.
2.
If the minimum length is 2, okay, I said one relation. If minimum length is n, at least n plus 1 state is required to design the DFA. Here, the minimum length string is 2. So how many state at least you require? How many state at least you require? Arul Karthik, are you in the line? Arul Karthik?
Yes, ma'am.
Are you in the line?
Yes, ma'am. Yes, ma'am.
I said if there are n length string is there, then the minimum number of states required to design the DFA is n plus 1. Okay. Here, the minimum length string is nothing but a first string length. First string length, you said 2. In 1 0, there are 2 symbol is there 2. So what is the minimum number of states is required to design the DFA?
2, ma'am.
If n means n plus 1, 2 means what?
3, ma'am.
3. What is this? So 3 status required. You see, this is the DFA. Q0, Q1 and Q2. 3 status required. The minimum length is 1 0. So from Q0 to Q1, there is a 1 transition. Q1 to 0, that is a 0 transition. First, you have to design the mission like that. Then you have to add more transition in order to validate the remaining strings of the language. Okay, you have to add more transition. So how we are adding this transition? When initially you have to add from Q0 to Q1, 1. Q1 to Q2 0. That is the initial transition you have to add. Okay. Then what you have to do is in Q1, okay, in Q1 you have to add a self loop 1. Why self loop 1 means? Because from Q1 already 0 outgoing is there. So you have to add a self loop over 1. Why self loop? Because there are 3 possibility. From Q1 to Q0 you can add 1. From Q1 to Q2 you add 1. But Q1 to Q1 itself you can add 1. Okay. So why from Q1 to Q0 there is no 1 means, okay, it will make the restriction over the length. So we avoid that. And there is a self loop over 1. Self loop means that it is not necessary. Compulsorily you have to read that self loop. Okay. You can skip on that. That is the kind of self loop. Okay. So similarly, you can add a self loop over Q2 because the condition here is the strings are ended by 0. So whatever number of 0 in the last end, there is no problem at all. Only we are checking whether the string is ended by 0 or not. So there is a self loop over Q2. Okay. So likewise, there are several missions here I have given as an example. For example, this is the question exactly asked in the gate. Design the DFA which accepts the language L is equal to 0 power n, where n mod 3 equal to 2 and n greater than or equal to 0. Okay. So what is this language? The language is the strings of 0 only. How the 0 is appeared? It is in the form of 0 power n. How the 0 is appeared? It is in the form of 0 power 1. What is the value of n? The n should be greater than or equal to 0. So the possible value of n are 0, 1, 2, 3, 4. All the possible value of n you have to take. And one more condition that n should satisfy. What is that condition? N mod 3 equal to 2. N mod 3 equal to 2 means that what? What do you mean by mod operator? You have to interpret all the things. Then only you understand what is the language. N mod 3 equal to 2 means whenever you are dividing n by 3, the remainder should be 2. Do you understand? So you take all the possible value of 0. All the possible value of n. Okay, I'm starting from the 0. 0 mod 3 value is 0. Because 0 cannot be divided by 3. So the remainder is that number itself. And 1 mod 3 equal to 1. Because 1 is also not divided by 3. So the remainder is that number itself. And 2 mod 3 is equal to 2. Because 2 is not divided by 3. So the remainder is that number itself. And 3 mod 3. 3 is completely divided by 3. So the remainder is 0. 4 mod 3 equal to 1. 4 mod 3 is 1. And 5 mod 2, 5 mod 3. This is 5 mod 3. 5 mod 3 is equal to 2. Likewise, it is going. Okay. Here I am highlighting something with red color. Why? Because the expected is n mod 3 equal to 2. If n mod 3 equal to 2, such n can be taken. So here, which are giving the reminders to 2 mod 3 is 2. So I'm highlighting that. That's 2 I can take. And 5 mod 3 equal to 2. 5 I can take because whenever 5 is divided by 3, the remainder will be 2. So the values of n satisfy the condition is 2, 5, 8, 11, 14. Likewise, it goes. So the L is equal to 0 power 2, 0 power n, sorry, 0 power 5, 0 power 8, 0 power 11. Okay. So power here means what? Power means how many times the respective symbol is repeated. So 0 power 2 is equal to 2, 0. 0 power 5 is equal to 5 zeros. 0 power 8 is 8 zeros. 0 power 11 is 11 zeros. Likewise, it is going. It is also the infinite language. So here I am designing this DFA starting from Q0 because here the basic string is what? 0, 0. The 0, 0 is also having length 2. For length 2, at least 3 state DFA is required because the condition is at least for n state, n length string, at least n plus 1 state is required. So for 2 length string, at least 3 state is required because we are deciding this number of state with respect to the length of basic string. What do you mean by basic string? The first string of the language. We are leaving the remaining one. But however, the DFA should accept all the remaining strings of the language once you complete all the transitions and states. Okay. So Q0, Q1 and Q2, from Q0 to Q1, 0 transition. From Q1 to Q2, 0 transition, and Q2 is the final state. On reading 2 zeros, the control comes to the final state. On reading the third 0, the control goes to Q2 to Q0. And fourth 0, Q0 to Q1. And fifth 0, it again comes to the final state. On 6th 0, it goes to Q2, 7th 0, Q1, and 8th 0, final state. So likewise, you can validate 2 number of 0, 5 number of 0, 8 number of 0, and 11, and some, it is going like, okay. And the next example is, we have to design the DFA which accepts those strings contain odd number of A's over sigma equal to A comma B. Odd number of A's over sigma equal to A comma B means your string is a combination of A's and B's. The length of the string, there is no constraint over the length, but the condition is the number of A's should be in an odd count. There is no condition over the count of B. The count of may be in odd or even. Did you understand? Okay. So now you take A is equal to 0 and B is equal to 1, because in order to write all the possible combination, definitely you are very confident with your digital. Okay. So in zeros and ones, you can able to write all the possible combination. So I convert this A into 0 and B into 1, so that it will be very easy for you to write all the possible combination. The combinations are, in length 0, epsilon is written. In length 1, 0 and 1 is written. In length 2, 0, 0, 0, 1, 1, 0, 1, 1, these are written. And length 3, likewise, they are written. Odd numbers means they are 1, 3, 5, 7. So, in every string, there should be the odd number of A is there. Okay. Then only that strings will be the member of the language accordingly. Okay. So if this is your language, you see the first string. What is that? Epsilon. Epsilon says there is the 0 number of A is there and 0 number of B is there. What do you mean by 0? That is a 0 means what? It is a even count. So epsilon is not at all a member because it is violating the condition. The condition is, in every string, there should be the odd number of A is there. Did you understand? Okay. You take a next string 0. What is that 0? 0 is actually A. That assumption we have take previous. Okay. 0 is A. So in that 0, there is only one number of A is there. Only one number of A is the odd number of A. B is not there. In 0, B is not there because B is not at all a matter. There is no constraint over how the B count is there. It may be an odd count or even count. So we can include A. The next string in our zeros and 1 combination is 1. 1 means what? It is B. Okay. Only one B is there, but there is no A. No A means 0 number of A's. No A means 0 number of A. 0 number of A means it is a what count? Even count. So we can exclude that B. A. Even count of A, we exclude. 0, 1, we can include because one number of A, one number of B is there. In 1, 0, we can include. BA, we can include because one number of A, one number of B is there. Did you understand? Likewise, we have to include some of the combination which satisfying the condition. So by eliminating some strings, finally we get these are all the member. A, B, BA, AA, likewise it goes. So from the language, what you understand, the basic string is the A. Okay, what is the length of the basic string? 1. So at least how many states you require? 2 states in order to design the DFA. And we called those 2 states are Q0 and Q1. And the Q0 is the initial state and Q1 is the final state. Did you understand? Next, we have to make a transition. So here, how I am making the transition means, on reading 1, 0, sorry, 1A means odd A. 1A, the control transfer from Q0 to Q1 and Q1 is a accepting state. On reading a single A, we enter into a final state. If suppose there is a possibility of reading second A from Q1, what you have to do is you have to direct the control to Q0. On reading the third A only, you can go to Q1. Okay. So for whatever odd count, the control comes to the accepting state. You understand? On first A, it goes to accepting state. Third A, it goes to accepting state. Fifth A. Likewise, odd count, it goes to the accepting state. And in every state, we add a self transition over B. Why? Because there is no control over how many number of B comes. It may be a 0 count, 1 count, 2 count, whatever the count may be. There is no control over how many number of B comes. Okay. So how we can make whether the DFA accepting any one string, we have to do a validation. As I already told here, I am taking one example. Okay. Single A. On reading a single A, the control goes from Q0 to Q1, so it is accepted. On reading AB, AB is a valid or invalid? It is a valid string because it contains only one A. Only one A means odd number of A. Odd number of A is accepted. So on reading AB, the control goes from Q0 to A. Okay, on reading A, the control goes from Q0 to Q1. Q0 to Q1. On reading B, the control stays in Q1 itself because there is a self transition from Q1 to Q1. Okay, control stays itself. Did you understand that? So finally we are end up with the Q1. It is accepting state. So the string, given string is accepted. Likewise, we can have a transitions. Okay. So very similarly, next example, it is a even number of A's. Okay. Then in next example, we have the design of DFA that accepts strings from sigma equal to A comma B, and the strings are ended by two consecutive B's. Strings are ended by two consecutive B's. So it is also the combination of A's and B's, but the condition is finally the string is ended by two B's. Two consecutive means two B's, consecutive B's. And there is no control over, okay, condition over whatever the symbols and how many number of times such symbols appearing before the two B's. Okay, are you understanding this? String is ended with two B's, but there is no condition over, okay, what is the combination of any symbols A or B before this 2B? There is no condition at all. So only the last two symbols is BB. So I can write the first string is in length to BB, okay, assuming that this BB is preceded by nothing, okay. And in second string, I'm writing ABB, assuming that the BB is preceded by the single symbol and that symbol itself A. So the resultant string I'm getting ABB, okay. Third, I'm assuming that the two B's are preceded by the single symbol and that symbol is a B. So the resultant string is BBB, okay. And the next string I'm writing in the length 4, the last two B's are preceded by two symbols. That two symbol you can make any combination. I'm writing the combination AA. In next I'm writing the combination AB. And third I can write a combination BA. And fourth I can write a combination BB. By that I can form the length 4 string. Similarly, you can have length 5, length 6 and goes. This is also the infinite string. Okay. As this is the language, first you have to study the strings of the language. What is the basic string here? BB is a basic string. This is the first string. What is the length of this BB? Okay, I'm asking what is the length of this BB? It is 2 because there are two symbols there. So at least how many state is required? 3 state at least. Okay, so this is the design. Okay, which is you have to start the design with 3 state initially. Q0 is the initial, Q1 and Q2, and you have to make a transition from Q0 to Q1 over B and Q1 to Q2 over B. Then you have to add a remaining transition in order to accept the remaining strings of the language. Okay, so the DFA design is very, very important. You have to apply your all the logics. Okay, this is actually the trial and error method. There is no uniform procedure is there. Okay, and after designing the DFA, you have to supply the valid strings to this DFA. All valid strings should be accepted and no one invalid string. No one invalid string is accepted. You understand? Okay. So this is very similar to what is the statement we have in the court. Okay. All the valid strings should be accepted. No one invalid string is accepted by the no one invalid string is accepted by the DFA. That is very important. Okay. So here the design DFA which accepts the strings of sigma equal to 0 A comma B, where the number of B's are divided by 3. Number of B's divided by 3 in the sense that number should be a multiple of 3. Okay. The number which is a multiple of 3 is definitely divided by 3. So I'm writing the numbers which are multiple of 3. They are 0, 3, 6, 9, 12. So this will be the, what is that? This will be the number of B's. This will be the number of B's in the combination A's and B's. Okay. So I start right, the first string is epsilon. Why means The epsilon tells there is a 0 times A, 0 times B is there. Here there is no condition on how many times the A is appear, only the condition on how many times the B is appear. How many times the B is appear? That number is equivalent to multiple of 3. They are giving the word, the number of B's are divided by 3. Okay, what is its equivalent? The numbers which are multiple of 3 are divided by 3 completely. Okay. So epsilon is a valid member. Why means in epsilon there is a 0 times A, 0 times B is there. 0 times A, there is no problem because there is no condition on number of A. 0 times B is also no problem because 0 is also the multiple of 3. Okay. The second string in length 1, you can write A alone. B alone you cannot write. Why B alone cannot be write? Because if you are writing B alone, that is a one time B is there. One time B is possible? No. Whatever times the B should be there. 0, 3, 6, 9, 12 like that. Okay, one time B is not at all possible here. Okay, so in length 1, A alone can be written. A alone says it has 1 A and 0 number of B. 0 number of B is accepted. In length 2, you can write, actually in length 2, what are all the combinations? You can have 4 combination, AA, AB, BA and BB. You can write AA alone. Why AB cannot be written? Because there one number of B is there. BA cannot be written because there is a one number of B is there. BB cannot be written because there are two number of B's there. The number of B's should be a multiple of 3. They are 0, 3, 6, 9 and 12. So that cannot be written. Likewise, in every possibility, you have to apply the condition and you have to write a valid string. Then you have to start the mission. Okay. So how here we are starting, that means here we see the languages consist of the combination of A's and B string. Okay, I started the design with the subset of the language so that the strings are only the combination of B's. Only the combination of B's, what are they? Epsilon, 3 B's, 6 B's and 9 B's likewise. Okay, so here the epsilon is a basic string. Basic string means that it is a length of 0. So how we freeze the number of states required for the design of DFA is 1? No, that is a minimum. That is a minimum length. So here I started the design with 3 states. So here your condition is failed. So that I said this is not exactly n plus 1, at least n plus 1. Many more state is required with respect to the complexity of your language. Here, even though the basic string is epsilon with 0 length, we are not freeze the design of DFA with 1 state. Okay, with the general principle of n state with n plus 1, n length with n plus 1. Okay, so n and n plus 1 is not exactly equal if there are n length strings and the minimum length is at least n plus 1. That is the relation. Okay, so only the combination of B's here I am making the mission. Then I add a self transition over every state on the symbol A so that the remaining strings are accepted by the DFA. Likewise, we have to design the DFA. And this is the next string. Here you have to design the DFA which accepts the strings and they have the substring AA. What do you mean by substring? Substring is nothing but any string which is preceded and followed by any number of, okay, preceded and followed by any number of the input symbols. Here the input symbols are A and B. So it is preceded by any number of A and B and followed by any number of A and B. Did you understand that? Okay. So I'm writing the basic string here, only AA. Why only AA? Because AA is a compulsory part. Okay, we cannot leave it. So in length 0, we cannot write the string epsilon. In length 1, we cannot write the string, that is single A and single B we cannot write. In length 2, we can write they are AA. Okay, AA alone, that is AA alone. In AA, we are assuming that it is preceded by nothing, 0 number of A's and B's. And it is followed by, there is no following symbol. So we are assuming that there is no following, means it is followed by 0 number of A's and B's. Okay. Next, you have to write the 3 length string. In 3 length string, AA is preceded by single A. AA is preceded by single B. Similarly, AA is followed by single A. AA is followed by single B. That you can write. Do you understand? So likewise, you can write the combination of AB so that it contains the substring AA. So here there is a procedure how the strings are formed. So in length 4, the AA is a substring. Substring maybe as the first part, the substring may be in the middle part, the substring may be at the end of the string. Any places the AA may be there in length 4. Okay, so these are the possibility. If A is the first part of the 4 length string, in third and fourth symbol you can write any. If A is the middle part, in first place and fourth place you can write any combination of AA. If AA is the last part, then the first 2 symbol you can write any. Okay, accordingly the mission is designed. Okay. So likewise, there will be the mission design. At least you have to clear about this DFA design. So next we can have a NFA design. When compared to DFA, NFA design is very easy. Why means here no condition we can follow, because from a state the input symbol may have any number of transition. Okay, so we have the liberal rule for framing the transition. There is no strict transition is there, because in case of a DFA you see that if from Q0, if the 0 transition is goes to Q1 and 1 transition is goes to, there is no more 0 transition from Q0. From Q0 the 0 transition goes to only one state. Okay, similarly from Q1 the 0 transition is going to only one state. On a symbol the output is going to only one state, but it is not a case in designing of DFA, so it is very easy to design. So let us have the first example. Design NFA for the language over sigma equal to 0, 1, and the strings of the language should be ended by 0. Strings of the language should be ended by 0 means, what is the first string? 0, because epsilon cannot be written. Why epsilon cannot be written? Because in epsilon there is no 0, no 1. Okay, but the condition here is every string should be ended by 0. So the first string here is 0, the second string here is 0, 0, and the third is 1, 0. In length 3, 0, 0, 0, 0, 1, 0, likewise we can write. So here the pattern is it should be ended with 0 preceded by any number of zeros and 1. Whenever the word any number is coming, we can use the pipe symbol as the operator or plus as the operator. Any number means it is closure. Okay, any number of what? It may be 0 or 1. Or this pipe symbol is read as R. Did you understand? The pattern is the 0 should be there. This is the compulsory portion. I am highlighting this compulsory portion with the green color. This is the compulsory portion, and that can be preceded by, why it can be preceded? Because the condition is the strings are ended by 0. Okay, the strings are ended by 0. Okay, so the 0 is preceded by any number of zeros and ones. 0 is preceded by any number of zeros and ones. Okay, this is the design. You see here the basic string is 0. So we can have the transition from Q0 to Q1 over 0. And the 0 is preceded by any number. Whenever the word any number is coming, we can add a self loop. Where we can add? Because before 0. So Q0 to Q0, there is a self loop. On what? On what we can add? It may be a 0 or 1, because in the closure here we are writing the 0 or 1. Okay, 0 or 1 we can add. So it is 0, 1. Okay, likewise we can have the next design is simple. Design NFA for the language over sigma equal to 0, 1, where the third symbol from the right of the string is 1. Third symbol from the right. Third symbol from the right. Okay, so see, in right I'm putting one red dot. That is the right end of any string. Okay, what is the condition they are giving? Third symbol from the right end should be 1. So before this dot we have the first symbol from the right. Okay, and before that symbol we have the second symbol from the right. Before that we have the third symbol from the right. I'm highlighting the third symbol from the right is by means of blue color. That should be 1. What about the first symbol from the right? No clue. So it may be 0 or 1. What about the second symbol from the right? No clue. So it may be 0 or 1. What about the fourth, fifth, sixth? Is there the possibility of forming fourth, fifth, and sixth symbols from the right? Yes, you can. You can form. There is no condition. any number of symbols you can form from the right to the left, okay, before this one as any combination of zeros and ones. So before this one, it is any combination of zeros and ones. Accordingly, we can write some strings of the language, then we can design the mission. Okay, see the mission from Q0 to Q1, 1 should be 1. Okay, because it is the third symbol from the right. And right here is this Q3 is a accepting state. So it is treated as a right end of the string. Okay, Q3 to Q2. Okay, Q3 to Q2. The communication between Q2 and Q3. Communication between Q2 and Q3 tells. Okay, it read the last symbol, or we can say it is the first symbol from the right. Okay, that is the communication which read first symbol from the right on 0 and 1. Then Q1, Q2, this transition tells the second symbol from the right. And Q0 to Q1 tells the third symbol from the right, it should be 1. Other than that, others are 0, 1. And there is a self loop over Q0 which says any number of zeros and ones comes before the third symbol on the right. Okay. Then this procedure you have to know, because in gate question what they are asked means they are given the language and they asked to write what is the minimum number of DFA states required. So directly designing DFA for the any language is somewhat difficult. If the language is readable, if the language is simple enough, you can easily design the DFA. Okay. So if you are not able to design the DFA directly, what you can do is you can design the NFA. Okay. From the NFA, you can convert the NFA into DFA. For example, if this is your DFA, PQRS, you are assuming that. If this is your DFA. Kindly note down, this is your DFA. Now I am converting this DFA into NFA. DFA into NFA, how to write. I have to design. Sorry, this is NFA. NFA is given. We have to form DFA from NFA. The reverse is not possible. Okay. How you can start design means in DFA also you have to find a transition. Okay. You draw the DFA transitions. Again, the state. There's input symbol 0 and 1. First, you have to write what is the initial state of DFA. The initial state of DFA is equivalent to initial state of NFA. So P is also the initial state, but we should understand that every DFA state is the set of NFA states. Every DFA state is a set of NFA states. So in order to understand those sets as a single state, we have to enclose the set of state by means of some square bracket, or you can write this P as it is. So what is the output you are having here? For P, the 0 output is in NFA, it is P comma Q. Here you have to write this is PQ. By combinedly, you have to write PQ, and you are assuming that this PQ is a single state DFA. For DFA, it is a single state. You have to assume this is the single state of DFA, even though it has more number of NFA states, and every component is treated as a single state. And from P to 1, it is P itself. What is the new state you find in the step 1? PQ. So that PQ is coming as a state of DFA. For PQ, you have to identify the transition on 0 and 1. So how you can make a transition on 0 and 1? Again, you have to go through P and Q zero transition. What is the zero transition on P? PQ. What is the Q zero transition on Q? It is R. You have to combinedly write here. It is PQR. It is PQR. That's all. Okay. Next here, for from P the one transition goes to P. From Q the one transition goes to R. So here the output is PR. But this PR and PQR is not a set of state. These are single state DFA. So the new state you find is here is PR. For the new state, you again process the transition. From PR, the transition will be PQS because you have to combine the output of P and R. Okay. So for 0, it is PQS. PQS. For 1, by combining P and R, there is the output P and null. By combining P and null, combining means that taking union. Okay. P union null, it is P alone. Okay. What is the new state here you encountered? PQS. So for PQS, it is PQ or S. PQ or S. PQ or S. For 1, it is PRS. For 1, it is PRS. So you encounter 2 states new, they are PQRS and PRS. These 2 new states you find. Okay, for these 2 new, you have to find a 0 and 1 transition. So for PQRS, the 0 transition will be what? You combine all the 4 0 transition output from NFA. P, Q, union R, union S, union S. What output you are getting? That is PQRS. Okay, in PQRS to 1, PQRS to 1, from P, 1 goes to P, from Q, 1 goes to R, S, 1 goes to S, from R, there is no one output transition. So by combining these 3, what you are getting, that is PRS. And in PRS, what is the 0 output? PRS, this is PQS. PQS. And for PRS, what is the 1 output? It is PS. And PS, I think, new state. Okay. PRS is already there. PQS is already there. PS is the new state. For PS, what is the 0 output? It is PQS. What is the 1 output? Yes. No more new state is encountered, we stop the procedure. Whenever no more new state is encountered, we stop the procedure. So this is how we are framing the DFA transition table. This is actually the DFA. So if your NFA has 4 state, here the DFA has how many state? 1, 2, 3, 4, 5, 6, 7. Number of state is equivalent to, for PQR, we are not taking the transition. PQR is also here new. PQR. QR or PQR, this is PQRS, PR. Okay. There are 8 state. I think no more new state is there. So here we mark the initial state. Which are all the final state? That also we have to mark. For NFA, the final state is yes. Wherever the name yes combination is there, those states are final state of DFA. Accordingly, this PQS has S component in it, so it is the final state. PQRS has S component in it, so that it is the final state. And PRS has the S component in it, so it is the final state. And PS has the S component in it, so it is the final state. Likewise, we can mark the final state. Did you understand? Okay. Actually, the relation between number of states in NFA and DFA is, if NFA has N state, the DFA has maximum of, not exactly again, maximum of 2 per N state. This relation is also you have to know. Maximum of 2 per N state you can make. This is the maximum. Okay. But practically less than 2 per N state is there. For example, here there are 4 states in this example, we have 4 states for this NFA. So maximum 2 power 4 is equal to what? 2 power 4 is equal to 16. Maximum 16 states we can form. But how many states actually formed? 8. Did you understand? So we are saying that this is the maximum count. Is it clear? This is you should know, because based on that there will be the question in gate. See, this is your NFA. Very similar to the DFA. In NFA also we can check the validity of the string, even though the diagram tells the transition over the input symbol. Okay, with the help of the extended transition function, we can have the transition over the strings. So assume that this is the NFA. I want to check whether the output string 01001 is accepted by this NFA or not. So how can we do? So here I insert one text box center. How you can do? You start your process from Q0. Okay, what is the first symbol you have to read? Because your given string is you see, which is highlighted in the red color. What is the first symbol you are reading? 0. From Q0, the 0 goes to where? From Q0, the 0 goes to, there are 2 output. You write all the 2 output. You write from Q0, the 0 goes to Q0 and Q3. Based on the diagram only I am writing. After that, you process the next symbol, which is nothing but 1. Okay. After processing 1, okay, you have to start processing 1 from Q0 and Q3. From 2 states you have to process. From 2 states you have to process. Is it clear what I am writing on the text box? From Q0, Q3, I have to process 1. Okay. From Q0, the 1 goes to again 2 states, Q0 and Q1. So I have to write that Q0 and Q1. From Q3, there is no 1 output. So I can close this. Next, I have to process from Q0, Q1, I have to process the third symbol, which is nothing but 0. So where it will be going, from Q0, the 0 goes to Q0 and Q3. And from Q1, the 0 goes to, there is no 0 output. So we close this. And from this, we have to process the fourth symbol 0. Where you are going, from Q0, the 0 goes to, from Q0, the 0 goes to Q0 and Q3. Then from Q3, the Q3 you have to take from the input. Okay. From Q3, the 0 goes to Q4. Okay. Next, from these 3 states, you have to process the last input symbol 1. From Q0, the 1 goes to Q0 and Q1. From Q3, the 1 goes to where? From Q3, there is no 1 output. From Q4, 1 goes to itself, Q4. After that, there is no more symbol is there in order to process. So finally, we are end up with which states? DFA, finally, we are end up with the single state. But it is a NFA. We end up with the collection of states. Okay. But in such situation, how can we make a decision whether the string is valid or invalid? In this situation also, we can take a decision. How means, so resultant set is actually Q0, Q1 and Q4. I'm highlighting this by red color, Q0, Q1 and Q4. What are all the final states of this NFA? There are two final states, Q2 and Q4. Either one of the final state is the member of the last stage, then we can conclude the given string is valid. Yes, Q4 is a member of the, one of the member of the last result. Q4 is one of the member of the last result. So we can conclude that the given is valid. In the final stage, if none of the final state is included, then we can conclude that the given string is a invalid one. By that way, we can make a validation of the NFA. And one more form of NFA here you have to see. That is the NFA with epsilon transition. NFA with epsilon transition means that already we see what is DFA and NFA. In DFA, purely it won't accept epsilon, and from every state or every input symbol, there may be the only one output is possible. In NFA, that is relaxing the condition. From a state, there may be more than one output is possible. Okay. And one more relaxation to that NFA is it allowing epsilon transition also. Epsilon transition is nothing but without reading the input, we can make a move from one state to another. That is called as epsilon transition. Without reading the input, we can have the ability to move from one state to another state. Normally in previous NFA and DFA, what we can do is on reading a particular input symbol only, we can make a move from one state to another. But here, without reading any input, we can move from one state to another. For example, there are two states P and Q here. Both are final state also. And there is an input transition over the symbol A and B. And there will be the epsilon transition from P to Q. There will be the epsilon transition from P to Q. That is the epsilon. Okay. That is the epsilon transition. So, without reading any input, if suppose my input is BB, for example. Okay. Even though I am not having B transition from the initial state P, but without reading any, I can go to immediately the state Q. On that Q state, I read two continuous B's and make a solution is that BB is accepted by the NFA. By that way, I can make a solution. Okay. If the point is clear, this is with respect to all kind of a finite automata. The next is with respect to the regular expressions and regular languages. This is also very important because we have the allied concept of finite automata in the regular expression. Okay. So in finite automata, we say finite automata is a mathematical model. The regular expression is a algebraic notation. Okay. That is a mathematical model, but it is an algebraic notation which is used to describe the language accepted by the finite automata. What is the language accepted by the finite automata? Those languages are expressed by the regular expression. So it is more powerful because within a single notation, it describes all the strings of the finite automata. And it is an expression. Okay. Normally, we came across the mathematical expression. What is mathematical expression? You can say 2 plus 5 is a mathematical expression. Why? Because there is a operator plus is there and operand 2 and 5 is there. Whenever the operator and operand are combined together, such is called as the expression, mathematical expression, because there is a mathematical value, mathematical operator. Here it is a regular expression, very similar to the mathematics. Regular expression, it is the combination of input symbol and regular expression operators. There are three regular expression operators are there. One is called as a union, another one is called as the concatenation, and next is called as the clean closure. There are three regular expressions operators are there. Okay, with respect to the priority, normally whenever we say the operator, definitely for evaluation, we have to apply the priority. Okay, here the top priority goes to clean closure, because always when compared to the binary operator, the unary operator has a more priority in normal mathematics also. Okay, if you have two operators, unary minus and multiplication, which has the highest priority? Unary minus has the highest priority. Always the unary operator has the highest priority. Accordingly, here the clean closure is the unary operator. But union and concatenations are binary operator. So this cleaning closure has the highest priority when compared to union and concatenation. Okay, and the union and concatenations are binary operators. The union has the lowest priority. Okay, next to highest priority is concatenation, and more priority is going to cleaning closure. And we can formally define the regular expression. Regular expression is formed from the input symbol and regular expression operators. So we can have null is also the valid regular expression. Why null? Because it is an empty language. Epsilon is also the valid regular expression. Why? Means it is a language consists of empty string. That is also the valid regular expression. Every symbol is a valid regular expression. Symbol A is also the valid regular expression. 0, valid regular expression. Any single symbol is a valid regular expression. And we can form the complex regular expression with the help of 3 operators. They are union, concatenation, and closure. If R and S are 2 regular expressions, then R plus S or pipe symbol S. Pipe symbol plus comma can be interchangeably used. You can make use of any, but mostly pipe symbol and plus, these two are used to denoting the union operator. R bar S. R bar S is a regular expression. Otherwise, R into S is a regular expression. R closure into a regular expression. Okay. Likewise, we can form a regular expression. So now this is the task of writing the regular expression. The language is given, you have to write a regular expression. Similarly, whenever the regular expression is given, you have to be able to interpret what is that regular expression, what is the language of such regular expression. So that is also we require, because in many of the gate question, they are simply giving the regular expression, 2 or 3 regular expression they are giving that, and they asked that whether those regular expression will represent the same language or not. Such kind of question is asked in the gate. So once you know how to expand the regular expression, expansion in the sense that how you can able to write all possible strings of the regular expression, then only you can compare whether the 2 or 3 regular expressions are equal to one another or not. Okay, are you able to clear? Okay, see this. You have to write a language for the regular expression A closure. Okay, language, you have to write a language in the sense that set of strings. So from A closure, what are all the strings generated? Any guess? What is A closure? You know the A closure is A power 0, union A power 1, union A power 2, union A power 3. Likewise, it goes, it is an infinite one. A power 0 is nothing but epsilon. Okay, A power 1 is nothing but what? Single A. Power here means how many times that symbol is repeated. A square means 2 times that is repeated. A cube means 3 times it is repeated. By taking the union of all, what you are getting? Epsilon, single A, 2A, 3A likewise. Okay. The next example, here you have to write a language for the regular expression A plus B the whole, A plus B into A closure. So whenever the concatenation is not explicitly given, you assume such operators are concatenation. In mathematics, you know, if you have the expression xy, xy means what? X into y. The multiplication is by default. So here the concatenation is by default. Okay. So here there is the expression A plus B, A closure. It means A plus B into A closure. Okay. So A closure we know that is the 0 and more occurrences of A. Before that you have to concatenate A plus B. So A plus B means A or B. Whenever A is concatenated with all this epsilon, single A, 2A, 3A, you are getting only the combination of A's. Whenever B, either A or B is concatenated, that is the meaning of this expression. Whenever B is concatenated with epsilon, we get what? B into epsilon. B, epsilon is a concatenation identity. You have to assume that whenever 1 is multiplied with any number, we are getting the same number itself in mathematics. So we called 1 is a multiplication identity. Okay, why multiplication? 1 is multiplication identity. Because whatever number multiplied with 1, we get the same number itself. Similarly, in automata theory, the epsilon is a concatenation identity. Whenever epsilon is concatenated with any input symbol, not only a single symbol, any expression itself, we are getting the same as a result. Okay. So whenever B is concatenated with epsilon, we get B. B is concatenated with A, we get BA. Okay. Likewise, we can form all the strings of the given expression. So next, we have to write a language for the regular expression A plus B, the whole closure. You know, whole closure is nothing but all the powers of the respective symbol. A plus B, here the symbol. A plus B, all power. All power means that A plus B the whole power 0. Union A plus B the whole power 1. Union A plus B the whole power 2. Likewise it goes. Okay. A plus B the whole power 0 means what? Anything power 0 is epsilon. Anything power 0 is epsilon. And A plus B the whole power 1. Either A or B is repeated only one time. Either A or B is repeated only one time. So the resultant will be A comma B. Okay. And A plus B the whole power 2. It is nothing but the A and B are repeated 2 times. A and B are repeated 2 times, which means length 2 strings are produced in the combination of A and B. And you know what are the length 2 strings in A and B? They are AA, AB, BA and BB. Likewise it goes. By combining all those, what you are getting? By combining all those, what you are getting? Epsilon, A, B, AA, AB, B, BA, BB, likewise it goes. Okay. And write a language for the regular expression A plus B the whole closure into A plus BB. How we can do? A plus B the whole closure already we have written in our previous case. And that will be concatenated with A plus BB. Either it is concatenated with A or it is concatenated with B. That is the meaning. Plus means or. Either it concatenated with A or it is concatenated with BB. Okay. Whenever it is concatenated with A, what the resultant set you have? Because you know what is A plus B the whole closure. This is epsilon A, B, AA, AB, BA and BB. Okay. Whenever it is multiplied with or not multiplication, I would say it is concatenation. So whenever it is concatenated with A, the A will be added as the last symbol in each of the string in A plus B the whole closure. So whenever epsilon is concatenated with A, I am getting A alone. Whenever A is concatenated with A, I am getting A alone or AA alone. And B is concatenated with A, I am getting BA. Similarly, epsilon can be concatenated with BA also. Epsilon into BB, BB. A into BB, ABB. B into BB, BBB. Okay, likewise, this length will goes. Did you understand? This will be the resultant language of the given expression. Okay. The next regular expression. Write a regular expression for the language of set of strings of 0 or more A's followed by 0 or more B's. Okay, 0 or more A. 0 or more A means what? A closure. Followed by 0 or more B's. 0 or more B means B closure. So the regular expression is nothing but A closure into B closure. Do you understand it? Write a regular expression for the language of the set of strings of zeros or more A's followed by 0 or more B's over sigma equal to A comma B. This is the question. The answer will be 0 or more A means it is A closure. 0 or more B means it is B closure. So A closure into B closure. And write a regular expression for the language of strings of zeros or more occurrences of AB over sigma equal to A comma B. Okay. One or more occurrences of AB. So it is AB closure. Okay. Write the regular expression for the language of strings of zeros and ones with at least 2 consecutive zeros. At least 2 consecutive zeros should be there, but it is a combination of zeros and ones. So 2 consecutive 0 in length 2, I am writing only 2 zeros. In length 3, how I can write? In length 3, this 2 zeros may preceded by one symbol or followed by one symbol. Okay, if it is preceded by one symbol means that I'm writing that pattern is dash 0 0 preceded by one symbol. In that dash, I can fill either 0 or 1, isn't it or not? So accordingly, I'm getting two strings. If I fill only a single 0, I'm getting entirely 3 0 because already two zeros are fixed. The condition is at least two consecutive 0 is there. So in length 2, 2 0 already written. In length 3, the two consecutive 0 either preceded by the single symbol or followed by the single symbol. If you assuming that the two zeros are preceded by the single symbol, then I am putting dash in front of two zeros. In that dash, I can able to fill either 0 or 1. So it will be 0 0 0 or 1 0 0. Okay, similarly, if two consecutive zeros are followed by one symbol means it may be three zeros or two zeros followed by one, because in that third symbol I can put either it is 0 or 1. Okay, likewise, length 4. Two zeros may be preceded by any of two symbols. Two zeros may be followed by any of two symbol, or middle way you can write 2 0. Sorry, middle way you can write 2 0. In front you can include one symbol, and following you can write one symbol. Likewise, you can include. Isn't it or not? Okay. So by combining all those, you get the language of the given expression. Did you understand? Okay. Then you have to write a regular expression. That is actually the question. So middle way, I can write 0 0. In front of that, I can write any combination of zeros and one, followed that any combination of zeros and ones, because the condition is only two consecutive 0 is there. So two consecutive 0 is the certainly part. Before that, any number of zeros and ones followed by any number of zeros and ones. And write a regular expression for the language of strings of zeros and ones with the substring 101. Substring 10. Okay. So 101 is the middle part, which is preceded by any number of zeros and ones followed by any number of zeros and ones. That's all. Okay. Write a regular expression for the language of strings of zeros and ones with even number of zeros. Even number of 0 means number of zeros should be in the count 0, 2, 4, 6. But there is no problem at all how many number of 1 is coming. Okay, it may be in the count 0, it may be in the count 1, 2, 3, 4, and all. Likewise, it goes. Okay, you write all the possible combination of zeros and ones and apply the conditions. Whichever the string doesn't obey the condition, you leave from the set. Okay, then you take the resultant. That will be easy for you. If you start applying the condition at the very first writing of the language, then it will be very difficult for you to come up with the final language in the correct way. So what you can do is you can write all the possible combination of zeros and ones starting from length 0, length 1, length 2, length 3, and likewise it goes because it is an infinite set. You take the first string here. What I am doing, epsilon is the first string. Okay, it consists of 0 number of zeros and 1 number of zeros. 0 number of 0 and 1 number of 0. Is it okay? I already write number of zeros per meter, number of ones per meter. Number of 0 is 0, number of 1 0 in epsilon. Yes, it is per meter range. So I can include it. Next symbol. Sorry, next string, it is 0. Next string, it is 0. What is that? It says only 1 0 is there. There is no 1 is there. Only 1 0 is allowed? No. One number of 0 is not allowed. So it is striked out. Next string 1. Next string 1 says there is a 0 times 0 is there, 1 time 1 is there. Yes, it is allowed. 0 times 0 is allowed. Okay, so we can include 0 0. In 0 0, 2 number of 0 is there. Yes, it is allowed. Okay, no matter on how many number of 1 is coming. Okay, the number of ones maybe it may be 0, 1, 2, 3, 4. There is no matter how many number of 1 is coming. And 1 1 in 1 1, sorry, in 0 1. 0 1, one number of 0 and one number of 1. One number of 0 is not allowed. So it is striked out. And 1 0. Okay. One number of 0 is there, striked out. 1 1, 0 number of 0 and 2 number of 1s allowed. So we can include. Likewise, we check the possibility of every string. And whatever the string striked out, that will be removed from the set. The remaining will be carried over in order to form the final language. Is it clear? Okay. So here we have to write a regular expression for that. The regular expression is, I'm writing the regular expression in two parts. Y means the one closure. You see the second part. Why one closure means that any combination of ones may come. There is no condition on the number of ones. So I'm separately writing this is one closure. Whenever there is a zeros and one combination is coming, okay, it may be epsilon or two zeros, four zeros, and six zeros, eight zeros. Okay, it is in the combination of that is multiples of two. So two zeros should be there. Okay, and it is not at all necessary two zeros should be in a consecutive manner. It may be in any order. So one zero may be preceded and followed by any number of ones. Similarly, the second zero is preceded and followed by any number of ones. So I'm writing the regular expression as one closure zero, one closure zero, one closure the whole closure. Why whole closure? Why the whole closure? Because epsilon is there. Okay, there is the epsilon is there. So this is the regular expression. So here we have to write a regular expression for the language of even length strings of zeros and ones in which zeros and ones are present alternatively. What it means? Zeros and ones present alternatively. That should be continuous zeros and ones. They are present in an alternative way. Epsilon, there is no zeros and ones. 0, 0, two zeros are continuously present. 0, 1, yes, alternate zeros and ones. 1, 0, yes, alternate 1 and 0. 1, 1, there is no. Okay. Likewise, we check the, okay, and this is the even length string. So length 0, length 2, length 4, that should be written. Okay. Whichever it is not satisfying the condition, we strike out, and the remaining will be carry over. So from this, you understand what will be the pattern of the strings. Epsilon is there, then there are the strings 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Likewise, it going. Similarly, which is highlighted in the green color, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. Likewise, there are two kind of patterns here. One is any combination of 0, 1. Another is any combination of 1, 0. Okay. So this is the regular expression. So kindly copy this 0, 1 closure, 0, 1 closure and 1, 0 closure. Okay. Similarly, we have the several examples for that. So this is actually the equivalence we have to discuss. What is the equivalence between finite automata and regular expression? Okay. And regular expression, we say this is the algebraic notation for expressing the language accepted by the finite automata. Okay. And this diagram shows the relationship. From regular expression, we can convert that into a epsilon NFA. Epsilon NFA can be converted into ordinary NFA and DFA. And NFA can be converted into DFA. In turn, DFA can be converted into NFA. Okay. So this is the relation between. Similarly, NFA is also directly converted into a DFA. Sorry, regular expressions. NFA is also converted into a regular expression directly. Did you understand? So this is how the relation between the regular expression and the finite automata. The algebraic laws of regular expression we should know, then only we can able to simplify the regular expressions. So these are the laws. Null plus R equal to R. Okay. These are the laws. I share this PPT, then you can understand how this laws can be interpreted. Very similar to the mathematical simplification. Here we have to understand the algebraic regular expression simplification. This null, you assume that this is 0 in mathematics. Whenever 0 is added to any value, we are getting the same value itself. 0 is multiplied with any value, we are getting 0. Like you understand this null. Null is like a 0 in mathematics. Likewise, you can map. Here, there are only two operators. One is plus, another one is the dot. Plus is the union, dot is the concatenation. And the epsilon, you understand this epsilon is a concatenation identity. In mathematics, you correlate this epsilon with 1 in mathematics. Whenever 1 is multiplied with any value, we are getting the same value. Okay. And epsilon closure is also epsilon. Whatever time you are applying the closure in epsilon, we are getting the epsilon itself. R plus R, if you are adding two R together, we are getting the single R, because union is called, plus is a union operator, and R is a language. The regular expression is actually the language. Language is a set. Whenever the set consists of the same number, by taking the union, only one time that will be represented. So R plus R is equal to R. Likewise, there are several laws is there, and which is I'm highlighting by red color. They are frequently used for simplification. So I highlighted those three by red colors. The next is very important, equivalence and minimization. Okay. Whenever the DFA is given, there is a possibility of minimizing the DFA. Minimization is nothing but reducing the number of states in DFA. How we can do a reduction? Okay. There is a procedure is there. So among the states in the DFA, we find some equivalent states among that. If some of the states are equivalent together, they can be combined together. Okay. For example, if you have the DFA of 5 states, and state 1 and 3, you assume that those two states are equivalent to one another, state 1 and 3. Instead of keeping the two states separately, you can combine those two states as a single state. 1 and 3 can be combined as 1, 3. So the two states will be reduced into a single state. Likewise, we can reducing the number of states. So why we have to do a reduction in the sense? By reducing the number of states, automatically the processing power of DFA will be improved. This is very similar to how we are doing the efficiency analysis in algorithms. In order to solve any problem, we have written some algorithm. The algorithm which comprises of minimal number of steps will do a performance better. Likewise, okay. So minimization. For that, you have to find the equivalent states. Okay. How we can find the equivalent state means if the states belongs to the same category, then there is a possibility of those states will be equivalent to one another. Belong to each category, same category means that there are two category of states. One category is a final states, other category is a non-final states. Okay. Actually, the states from different category should not be equivalent. They are distinguishable. Distinguishables are called as a non-equivalent states. Okay. And there are several algorithms are there in order to find the equivalent states. One familiar algorithm is table filling. I will explain how the table filling algorithm will find the equivalent. Why this will be interested means because this kind of question is asked in GATE. They are giving one DFA diagram is itself given, and the four choices are given from the DFA, which will be the equivalent DFA for the given DFA. Okay, such kind of question is asked in the GATE. For that, what you have to do is with the help of table filling algorithm. Okay, you have to work out. That is a 2-mark question in DFA. You have to work out. That is with the help of table filling algorithm. First, you have to find the equivalent states in DFA, and you have to merge those two equivalent states. Likewise, you can reduce the DFA state, and which will be the answer for you. That will be the option in the given. Okay, so by that you can give the answer for the question. Okay, so the table filling algorithm that find the actually the distinguishable state, that is not find the equivalent, that find the distinguishable. Distinguishable means that non-equivalent state. The states which are not marked as distinguishable are considered as a Equivalent state. By that, we are finding the equivalent states with the help of the table filling algorithm. Did you understand that? Okay. Distinguishable state means non-equivalent states. Okay. I will tell with the help of the example how you can find the distinguishable states. You see the problem here. Okay, the problem is given, minimize the following DFA. There are actually 8 states in the DFA. Okay. There are actually 8 states. This is the output. Okay. What you have to do is the states are named from A to H. There are the 8 states. So you have to form the table structure like this. Okay. Is it very clear to you? Table structure. That is state number 1 to state number n minus 1 is named in the bottom row. In the first column, you have to name the second state name to 8th state name. Okay. First state name to n minus 1 state name, it should be named in the bottom row. A, B. Normally A to H is the name. You have to name A, B, C, D, E, F, G. Okay. You leave H. And in first column, you leave A. First state, you leave A. You start from B. B, C, D, E, F, G, H. See the first column. And in every cell, I put a cross mark. Okay. This cross mark tells every cell is a pair. Okay. If you see, I'm highlighting the first one. I'm highlighting the first one with the help of the green color. That is the first cell. That cell is called as the AB or BA. In any way, you can read that. Okay. Every cell is a pair of state. Every cell is a pair of state. You can call it any name. Every cell is a pair of state. Did you understand that? Okay. AB is a pair. AC is a pair. AD is a pair. Okay. So how you are putting this cross mark means you see there are 8 states. Among the 8 states, D is a final, remaining all are non-final state. D is a final, remaining all are non-final. Whenever A is paired with D, definitely there is a not equivalent state because A belongs to non-accepting and D is accepting. Whenever B is paired with D, BD is a non-equivalent pair because B is a non-accepting, D is accepting. One accepting, one non-accepting is paired, such thing will be marked as distinguishable immediately. Okay, is it clear? So accordingly, this AD, okay, this AD, this BD, okay, and CD and DE and this DF and this GD and this HD, these are marked as distinguishable in step 1 of table filling algorithm. These are marked as distinguishable pair in a table filling algorithm. Okay. Next, how the remaining pairs are marked as distinguishable means that all the leftover pair will be written here. Input pair, I am calling that as input pair AB. Leftover pair means which is not highlighted by this green color, all are leftover. AB, AC, AE, AF, AG, AH, similarly all pair. I am listing all the pair here. For every pair, I have to find the 0 and 1 output. How the 0 and 1 output can be determined, that is also very easy. For AB pair, okay, you see the diagram or table. For AB pair, you AB for A and B from the given DFA. From A, the 0 output is going to B. From B, the 0 output is going to A. By combining these two, what you are getting? BA. Similarly, for one output, from A, one goes to A. For B, one goes to C. By combining these two, what you are getting? AC. So BA and AC will be the output. Here you have to write BA and AC. Likewise, for all the input pair, you have to write output. Once it is written, you see the output. Now, for every row, you have to process this table row by row. For every row, you see the output. Whether this output is marked as distinguishable already, then the input is also marked distinguishable. This is the step you have to follow. For example, in first step, AB is not at all marked as distinguishable. AC is also not at all marked as distinguishable. So we cannot mark AB as distinguishable. But the case in row 2, the BD here, it is marked as distinguishable by green color, you see. So since the one of the output is distinguishable, the input per AC is also distinguishable. I striked out. Likewise, I have to follow the steps recursively, and this is a recursive procedure. Until no more pair is marked as distinguishable, I have to do this step recursively. Finally, I left with AG, BF, and CE. These are all the pairs I left with. You see, these are all the pairs I left with AG, BF, and CE. So it says this AG is equivalent to one another and BF is equivalent to one another, C is equivalent to one another. So how I can mark a minimum DFA means this AG, I combine the states A and G together. Instead of having two states A and G, I am having A and G together. Instead of having B and F, I am combining the states B and F. Instead of having C and E, I am having the states C, E, D separately. It cannot be combined, and H separately. Based on this, I have to write output also. For AG, what is the output? Again, you see the original table. For A, the zero output is going to B. Here, there is no B is there. Okay, instead of B, here we have BF only. So, wherever the name B and F is there, we have to replace such thing by BF. Wherever the name A and G separately is there, such names are replaced by AG. Wherever the name C and E separately is there, and we have the name CE here. Likewise, we have to write output. Okay. Did you understand or not? Okay. So checking two DFAs are equivalent. This is also important. You are provided with two DFAs. Okay. For example, the first DFA D1, which has two states, and DFA to D2, three states. Okay. How we are checking the equivalence of two DFA means if the start state of two DFAs are equivalent, then the two DFA are equivalent. If the start state of two DFA is equivalent, then the two DFA is equivalent to one another. So first you have to check whether the start state of two DFAs are belongs to the same category. Yes, both belongs to the accepting category. You see, the start state A of D1 is double circled. The start state of X of D2 is double circled. So both belongs to the accepting category. So there may be the possibility of that they may be a equivalent. There may be the possibility. If two states belongs to the same category, we cannot certainly tell they are equivalent. There may be the possibility. Did you understand? So how we can check whether these two DFAs are equivalent? By treating these two DFA as a single DFA. You combine the state A, B, X, Y, Z. You have these 5 state as a single DFA 5 state, and make the table filling algorithm how we are marking the distinguishable state. Based on that, you see whether the start state entry means AX pair. What is the entry on AX pair, which is here I am highlighting by blue color. If the AX pair is equivalent, the two DFAs are equivalent. But here AX pair is what? Distinguishable. If AX pair is distinguishable, the two DFAs are not equivalent. This is the procedure how we check the two DFAs are equivalent to one another. Okay. The next with respect to the pumping lemma for regular language. Pumping lemma for regular language. Lemma is called as the short theorem. The pumping lemma is a powerful technique which is used to prove certain languages are not regular. So here I'm saying pumping lemma for regular language. Similarly, there are pumping lemma for context-free languages also there. Okay. So they check whether the language is not context-free. So here it checks the languages are not regular. Okay. So this is the definition of the regular language. First you see what is regular language. Regular language means the language which is accepted by DFA, NFA and epsilon NFA is known as regular language, or the languages which are expressed by the regular expressions are called regular languages. Okay. So for regular languages, only three operators are permitted. They are union, concatenation and closure. Okay. Other operators are there. Definitely they are not at all regular languages. Relating to pumping lemma, there are so many questions in GATE. They are giving 2 or 3 languages and they asked to check whether the language 1, language 2 are regular or not regular. They are telling like that. Similarly, there are questions are there. So you have to understand what is regular language and the pumping lemma, which is used to check the languages are not regular. Okay. So how we can check the language is not regular? The language, if L is regular in the sense, for every string W belongs to the L, that W can be split into 3 substring X, Y, Z. In order to split W into 3 substring, one condition you have to mainly concentrate, that is the middle string W. I'm writing that is the first condition. The middle string W, that should not be epsilon. Okay. Whenever you are splitting the string into 3 substring, the middle string should not be epsilon. Okay. When you are pumping means generating. Pumping in the sense generating. Okay. The XYZ is generated as XY power KZ. What is the value of K means? The K may take the value from 0 onwards. The K may take the value from 0 onwards. You have to pump the string XY power KZ. All the pumping or all the generated strings should belongs to L. Then we can say L is regular. Now we have to prove how the languages are not regular, because the pumping lemma is used to check the languages are not regular. Here there are example and the solutions are, here there is a solution. You see, prove the language L, 0 power n, 1 power n, and n greater than or equal to 1 is not regular using pumping lemma. Here I am going to prove the language with the help of the proof by contradiction. I assume the language L, 0 power 1 n, 1 power n is regular. What I'm doing is I'm generating the language L. Okay, I'm generating the language L. I'm substituting the possible value of n in place of 0n, 1 power n, and n greater than or equal to 1. Okay, so if n is 1, it is 0 power 1, 1 power 1. 0 power 1 means 1 times 0. 1 power 1 means 1 times 0. And 0 power 2, 1 power 2 means 2 0 2 1. 0 power 3, 1 power 3 means 3 0 3 1. So these are all the strings of the language. You see L. Let W is equal to 0 1. W equal to 0 1. I am taking any string. Here I am taking the first string. It is not at all necessary. You always concentrate on the first string. You can take any string. It may be a first string, second string, whatever the case. But always you concentrate on the minimum length string. That will be easy for you to prove the language is not regular. And you have to split this W into 0 1. Okay. This W into 0 1 means the W will be split into X, Y, Z. Actually, there are only 2 symbol is there. This 2 symbol will be shared to all these 3 substrings. So I am taking X is equal to epsilon, because the condition is that Y should not be epsilon. X is epsilon, Y is 0 1, and Z is epsilon. Or otherwise, other possibilities are how you are splitting. X may be 0, Y may be 0, Z may be epsilon. Other possibility of splitting is X is equal to epsilon, Y is equal to 0, Z is equal to 1. I am writing all the 3 possibility of splitting the string, but I am considering the first split. You can take any. That is your wish. You can divide the string at any. But when concatenating X, Y, Z, you should get the given W. The order should not be changed. Once you divide the W into X, Y, Z, next you start pumping. Pumping the string means X, Y per K, Z should be generated. Okay, when K equal to 0, you have to generate X, Y per 0, Z. That will be X is nothing but epsilon, as we already assumed. And Y is 0 power 1 into epsilon. 0 power 1 epsilon means it is epsilon, because anything power 0 is epsilon. So epsilon into epsilon, the resultant will be epsilon. Actually, epsilon is not belongs to the language, because the languages start from the string 0 1. Epsilon is not at all a member. So this contradicts the assumption. So the given language is not regular. By this way, you have to prove. Okay, by this way, you have to prove. Is it clear? Is it clear to you? By this way, you have to prove. So this is how you can prove the language is not regular. Likewise, I'm giving some of the examples. The next is very important. That is the closure properties of regular languages. Closure means when the languages are actually called as a set. So we can say the set is closed under any operation if applying that operation, okay, in any member of the set, always yield the member of the set, then we can say it is closed. What example we can have? That is, the positive numbers or integers are closed under addition and multiplication, but not division. Why? When you are adding two positive integer, the resultant is a positive integer. When you are multiplying the two positive integer, you are getting the positive integer as a result. Okay, but the operation is not closed under division. When you are dividing two, what do you mean by positive integers? Positive integers are plus 1, plus 2, plus 3, plus 4, plus 5. Whole numbers. Integers are actually whole numbers. Okay. 2 by 3, these are rational number. Okay. Integers are the whole numbers. When you are multiplying two whole numbers, you are getting only the whole number. When you are adding the two whole number, you are getting the whole number as a result. But when you are dividing two whole number, you are not at all always getting the whole number as a result. For example, 5 by 2. 5 is the whole number, 2 is the whole number. 5 by 2 is actually 2.5. Okay, we cannot guarantee that the resultant will be a whole number in division. So we can say the positive integers are not closed under division. Okay, so closure properties means that whenever you are applying any operation to the regular languages, the resultant is also regular. We say the regular languages are closed under such operation. Did you understand that? Okay, so in general, the regular languages are closed under union, because whenever you are unioning two regular languages, the resultant is also regular. Do you understand? Okay. How you are proving this means, if you have two regular languages, either you express two regular languages by means of a finite automata, and you can take a union. If two finite automatas are union together, what the thing you can do? Or otherwise, if you have two regular languages, you express those two regular languages by regular expressions. Then you apply the union. For example, you separately have the regular expression for the language A close. What are more occurrences of A? What is that? It is A plus. And other regular language, it is 0 or more occurrences of B. What is that? It is a B closure. What is the union of it? A plus union B closure will yield A plus plus B closure. Anyhow, you are getting the regular expression as the result. Whenever two regular expressions are operated, if you are able to get the regular expression, then we can say the regular languages are closed under some operation. So this is closed under union, closed under concatenation, closed under Kleene closure, and the regular languages are closed under intersection also. Okay, so in order to prove how the regular languages are closed under intersection, what you have to do is you have to take two DFA. For example, for the first DFA and second DFA. The first DFA representing one regular language, because whenever the language, okay, whenever the language is designed by the finite automata, such languages are always regular. Okay, if you have two finite automata, then the intersected finite automata, how you are making that? If you have two states in first DFA and two states in second DFA, you have to take a Cartesian product of states. A and C, one state. A and D, another state. B and C, one state. B and D, another state. There are four total state. Okay. Do you understand? This is 2 into 2, totally 4 state. And the product name as in the name of the Cartesian product names. Okay. And the transition from A to AC to AD. How we are making the transition? A to 0, where it is going A. Okay. From C to 0, where it is going D. So the output will be AD. Likewise, you have to make a output transition. And here the initial state is the initial state of first DFA and the initial state of second DFA. What is that? AC. And the final states is the final state of first DFA, which is intersected with the final state of second DFA. That is nothing but a BC. So BC is the final state of the product DFA. Okay. Closure under difference. Okay. If you have two regular languages, L and M, then we can have L minus M is also regular. Okay. Why? Because L minus M can be, L minus M is nothing but the strings in L but not in M. Okay. So if you have two DFAs AB for the language L and M, first you have to construct C, that is a product automation of A and B. So make the final state of C be the pairs where A state is final but B is not final. That is called as L minus M. Is it clear? Actually, product automation you have to make very similar to the previous. The product automation where you have to make. But here in previous, what is the final state? The pair, which is the final state of DFA1 and DFA2. That is the final state in the intersection. But in difference, how we are making the final state means the pair which are the final state of A but not a final state of B. Likewise, you have to make a final state. You see this example, again the same example, but here the final status in B but not final state in D. So what is the pair? That is BD. That is the final state for the difference. Next is complement. Complement means that if you have the language L, whether L bar is closure, that is closed or not. Yes, L bar is closed. Why means because L bar is equivalent to epsilon closure minus L. Epsilon closure is a regular, we know. L is given, that is regular. And epsilon closure minus L, already we know the regular languages are closed and a difference. So epsilon closure minus L is regular language. So L bar is regular. Likewise, we have to make. And reverses of the regular language. Yes, reverse of regular language is also regular. If you have the language L, we can make LR. LR is also regular. And this is the example how we can make a LR, that is a reverse of the regular expression. Okay. If F plus G is a regular expression, okay, then the reverse of F plus G is FR. You have to apply the reversal for F and reversal for G, then they will be union together. FG is a regular expression. By applying reversal, you are getting GRFR. If you have F closure as a regular expression, then F for the whole closure is a resultant reversal regular expression. And homomorphism, the closure, that is the regular languages are closed under homomorphism also. Homomorphism is called as a substitution. Substitution is nothing but any symbol over the alphabet is substituted by some length of the string. For example, here you assume the input symbols are 0 and 1. The 0 is substituted by the string AB and 1 is substituted by the string epsilon. Okay. Suppose you have actual string 0, 1, 0, 1, 0. You see the last line of the example. So what is the homomorphic value of the 0, 1, 0, 1, 0 means? For every 0, you have to write AB because h of 0 is AB. For every 1, you have to write epsilon. So it will be interpreted as AB into epsilon into AB into epsilon into AB. That is AB into epsilon. See, it is AB into epsilon into AB, into AB into epsilon into AB. By concatenation, all those what you are getting. Because epsilon is a concatenation identity, already we discussed. So by concatenating all those, you are getting AB, AB, AB. That is the result. This is the homomorphic. The homomorphic, under homomorphism and inverse homomorphism, the regular languages are regular. Okay. Let us discuss some of the questions in GATE. See the first question. Let S and T be the languages over A comma B. Over A comma B means the language is the combination of the strings of A and B, represented by the regular expression A plus B the whole closure, and A plus B the whole closure respectively. Which of the following is true? S is the language of A plus B the whole closure, whole closure. T is the language of A plus B the whole closure. Which of the answer? The answer C is correct. Both S and T are equal because both the languages are generating all the combinations of zeros and ones. Okay. And the second, given an arbitrary non-deterministic finite automata, okay, it is NFA with n state, what is the maximum number of states in an equivalent minimized DFA is at least. What is the maximum number of states? I already write a relation. If NFA consists of, in our example, example of converting NFA into DFA, we have seen if NFA has 4 states, the maximum number of states in DFA is 16. The relation is, if NFA has n state, maximum number of DFA states are 2 power n. Okay, 2 power n. So what is the answer? B, 2 power n. Okay. See the third one. Let n be a NFA with n states. Let k be the states of minimal DFA. What is the equivalent to NFA? Which of the following is necessarily true? This is also a gate question, very similar to the second one. N is the number of states in NFA. K is the number of states in DFA. Okay. So actual DFA states K should be less than or equal to 2 power n because the maximum number of states in the DFA is 2 power n. So K is less than or equal to 2 power n. The option 4th is the correct one. Okay. If all the states of NFA are accepting states, then the language accepted by the NFA is sigma closure, true or false. All the NFA states are accepting, then the language accepted by the NFA sigma closure is true or false? It is false. If all are accepting state, okay, the epsilon is also accepted. Did you understand? The number of states in minimal deterministic finite automata corresponding to the regular expression. We have seen what is the minimal number of, I asked the question with respect to the minimum length string, what is the minimum number of states required? That is asked in gate. So this 0 plus 1, the whole closure, this is not at all a compulsory part. Okay. Closure means it is epsilon. But this 1 0 is a compulsory part. 1 0 consists of how many symbols in it? 2 symbols. 2 symbol is the minimum length. So at least how it is, what is the number required in a deterministic DFA? It is 3. If there are n state, then n plus 1 states, n symbol, there are n plus 1 states are required. So answer is 3. Okay. You see, again, the same question is in different format. 6th question. Let W be any of the string n, 0 and 1 closure. What it means? It is the combination of zeros and ones. It is the combination of zeros and ones. Let L be the set of all substrings of W. Okay, L is the set of all substrings of W. L is the language. What is the minimum number of states in non-deterministic finite automata that accepts L? What is the length of the string W? N. What is the question asked? The minimum number of states in non-deterministic finite automata. So, if the string of length W is N, the minimum is required is N plus 1. Okay. See this. The minimum state deterministic finite automata accepting the language L is equal to W. The W belongs to 0, 1, the whole closure. It just means that the string is the combination of 0 and 1. String is the combination of 0 and 1. And number of zeros and number of ones in W are divisible by 3 and 5. Number of zeros and number of ones in W are divisible by 3 and 5. So what is the length of the string? The length of the string should be divided by 3 and 5. So what you have to take? You should take the LCM value of 3 and 5. What is the LCM of 3 and 5? 15. Okay. So the length of the W is at least, not at least, it is a multiple of 15. 0 length, 15 length, 30 length, 45 length. So if this is the case, the minimum number of states required are 15 states. Is it clear to you? Is it clear? Likewise, you have to identify. Consider the following finite state mission. The finite automata is given. So they asked, what is the language accepted by the finite automata? What is the language accepted by the finite automata? You see, there are two final state is there, Q1 and Q2. With respect to these two states, you have to tell. Okay, for example, in order to reach the first state, in order to reach the first final state Q1, what you have to process? In Q0, there is a self loop. B. Self loop is nothing but B closure. So B closure into A, from Q0 to Q1 into A. Did you understand? Okay. Followed by, you assume Q1, Q2 alone is the DFA. In between Q1, Q2, what is the communication has happened? There is any number of A's and B's. You see, there is a self loop over Q1, there is a self loop over Q2, and from Q1 to Q2, A combination, Q2 to Q1, there is a A combination. Do you understand? There is a any combination. So the answer is B closure into A into B, A plus B the whole closure, all the combination. Is it clear? Okay. The smallest finite automata which accepts the language L is equal to X, where length of the X is divisible by 3. Okay. This is also we came across. Length of the X, that is nothing but length of the string. Divisible by 3 means multiple of 3. Multiple of 3 means the length of the string is 0, 3, 6, 9 and all. Okay, 0, 3, 6, 9 and all. So what is the minimum number of state is required? 3 state at least we require. We already discussed about the diagram. Okay, so with respect to the minimal number of state required, how many questions is asked? You see. Okay, I share this question. You try to answer. The answer is also given. Based on that, you can check. Can you understand that? Okay. Zaidul ma'am.
Yes, ma'am.
Ma'am, shall we wind up?
Ma'am?
Ma'am, shall we wind up, ma'am?
Yes, ma'am. Oh, okay, ma'am. Wait, ma'am. I'll ask. I'll call HOD, ma'am.
Okay, ma'am. Until then, I will discuss some of the questions, ma'am.
Okay.
Okay. So here also you see, let L be the set of all binary string whose last symbol are the same. The number of states in the minimum state deterministic finite automata L. Okay. The last two symbols are the same. What it means? All binary string. So it is a binary string means that it is a combination of zeros and ones. The last two symbols are the same means it may be either two zeros or it may be either two ones. Did you understand? This is the basic strings. Accordingly, you have to form the remaining strings of the language. It may be a length 2, length 3, length 4, length 5. Likewise, you have to frame the strings. Did you understand? In order to that is accept two zeros or two ones, in order to accept two zeros or two ones, what you have to require? To read a two zeros, you require a three states. Okay. In order to read two ones, you require again three states, but the initial states are glubbed. 3 plus 3 actually 6. The initial state is glubbed. So it is called as the states 5. Okay. And the number of substrings that can be formed from a character string of length n is normally what all the combination in length n, it is n into n plus 1 divided by 2. Can you understand? So kindly work out the questions given, and similarly you refer much of the questions from the net. So whatever you have, doubt you have, definitely you can contact me through your Zainul ma'am. Okay. So thank you very much for listening. Any doubts in this session? Any doubts? At least you learn something else, because I understand definitely this subject is new to you. So by just observing all the thing, you cannot understand all the things. You have to work out with the help of pen and paper the problem you have to solve. Even though it is a multiple choice question, For even 1 mark also, you have to work out and answer. Okay, because here I have seen some, I have shown some of the questions to you. So for all the questions, you have to frame the language and you have to find the states and all. Okay, so without working, we cannot choose what is the minimal number of required for the example problem.
Ma'am, can you
Yes,
please keep the front page of your first page of PPT, ma'am?
yes,
I'll
ma'am.
take screenshot. Students, anybody can give feedback for this session. Do you understand the concepts? Yeah, thank you, Arul Karthik. Can unmute your mic and talk.
Ma'am,
Listen,
shall
this.
I resume my slideshow?
Yes, ma'am.
Okay, thank you, ma'am.
Ma'am?
Yes, ma'am.
Yes, ma'am. We can wind up, ma'am. Actually, ma'am is little busy with some other work, ma'am.
Okay,
So,
okay, ma'am. Thank you very much,
thank you
ma'am.
so. Yeah, thank you so much, ma'am.
Mm.
Like students will get um, starting point of this session as to study the TOC subject, ma'am. So they'll prepare well for GATE exam with this sessions, ma'am. I mean, you please give your PPT slides and the questions you
Questions.
have
Okay, ma'am.
taken.
Definitely, I will share all the things with you, ma'am. Okay.
Okay, ma'am.
So
Okay, ma'am.
thank you very much for
Thank
inviting
you
and
so
thank
much.
you very much for listening. Thank you, ma'am. Thank you, ma'am.
Thank you so much. Yeah, thank you, students. You can lead the session. Yeah, thank you all. You can lead the session.